everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the types of optical fiber. So if we see at the brief outline of module 3, part 1 we have covered laser, and in part 2 we are discussing fiber optics. And in fiber optics, in the previous lectures, we have seen the principle, construction and working of optical fiber. And then we have also derived expressions for the acceptance angle and numerical aperture. Today we are going to see about different types of optical fiber. So if you see the outline of today's topic, types of optical fiber, first we will see the classification based on the mode of propagation. Then we will see the classification based on refractive index of the materials used. And then we will also see the classification based on the type of materials we are using. Now coming to the classification. So based on the refractive index of the core. So when we have seen the structure of optical fiber, we have seen that there are three important parts in an optical fiber. The first one is the core. The core is surrounded by cladding, and then we have the protective layers, which we call them as the coating. So when we have a core, suppose this is the core, and this is surrounded by a cladding. Now whenever we talk about the signal traveling through the optical fiber, it is through the core it travels. So based on the refractive index of the core, so we are talking here about the refractive index of the core, so which is the carrier of the signal. Optical fibers are classified into two types. The first one is step index fiber and the second one is graded index fiber. So based on refractive index, we are going to classify them into two types, the step index fiber and the graded index fiber. So the next classification is based on the number of modes of transmission. So based on the number of modes of transmission, again, we are going to classify it into two categories. The first one is single mode fiber, means when the transmission is in a single mode. And then we also have multimode. Multimode means more than one, here we are talking about. So this is how we classify it based on the number of modes of transmission, single mode and multimode. Now coming to the material used. The material that we are using for the core and the cladding. So we are mainly talking here about three things. I said the core, the cladding, and then you also have a protective coating. So when we are talking about the core and cladding, we have already seen and discussed the conditions for the core and cladding. Now we are going to talk about the material. So now the first one is all glass fibers, means the core is also made up of glass and the cladding is also made up of glass. Means we have a glass core. This is the first type, glass core with the glass cladding. So the first type we are talking about. So all glass means the core is also made up of glass and the cladding is also made up of glass. So both are glass. Then we have all plastic. All plastic here means core is made up of plastic and cladding is also made up of plastic. So this we call them as all plastic fibers. And the third category, we have a glass core with plastic cladding. So here in the third category, what we have, the core will be made up of glass and the cladding will be made up of plastic. So glass core with plastic cladding. And then polymer clad silica fibers. So here when we are talking about polymer clad, usually we'll have the core with silica. That is one type of glass, and then we'll have a polymer type of plastic. So this also we have. So these are the 4 types we are discussing. So but most of the times what we are using is a glass core with plastic cladding. So the classification should be clear first for us to understand how they function. So first one is based on the refractive index. 2 types, step index and graded index. The second classification based on the number of modes of propagation or transmission. If the light travels in a single mode, we have single mode fiber, and more than one we call it as multi-mode. And then based on the material used, we have all glass, all plastic, then we have glass core with plastic cladding and polymer clad silica fibers. So now let us discuss about each one in detail. So now based on the mode of propagation. So first we are going to discuss the types based on mode of propagation. So based on the mode of propagation, they are divided into single mode and multi-mode. 2 types we have. So the first one is single mode. So what is single mode here? We'll see here in the diagram, there is only a single mode of transmission. And in multi-mode, if you see, there are a number of modes of transmission. Now, mode here means what? The number of paths available for light propagation in the fiber. So, when we have discussed the light, which is the carrier of the signal, travels through the core. So, if that light travels along a single path, then we call it as a single mode fiber. So, depending upon the number of paths available for light propagation, we are going to classify them as single mode and double mode or multi-mode. If there is only one path, you call it as single mode fiber. If the light is being propagated only along a single path. See here in single mode fiber, if you see, this is the how the light, if you see this blue part, you see here, this is the core and this part is the cladding, because the core is surrounded by a cladding. It is cylindrical, but here we are seeing the cross section of it. So we have the cladding. This is also cladding. Core and cladding. So light propagates through the fiber in single mode. There is only one path. This is the single path for propagation. So you will call this as single mode fiber. If there are a number of paths here means more than one. It can be 2, 3 or many. Then you call it as multi-mode fiber. So now we see this multi-mode fiber. You see here, this blue part, as I said, is the core. You can also see the difference. Now I'll explain you the difference between the two. This is the core and this gray part is the cladding. Here also you have the cladding. So now how is the light propagating through the optical fiber? If you see, this is one mode, the light is getting reflected. We also have seen the principle on which it works. And maybe another one. This is how it reflects. And this is another one. So we are seeing many modes. So different modes of propagation, you will call it as multi-mode fiber. Now, if you look at the difference here, what we understand here is in single mode fiber, the diameter of the core is very small, very, very small. So only one mode can pass. That is why we call it as single mode fiber. And if you see, the diameter of the cladding is large. So this is the cladding. Coming to multi-mode fiber, so this is the diameter of the core. For the core diameter is large. So it allows many modes. or many paths to propagate through it. This is the cladding. So the basic difference lies in the diameters of the core and the cladding. So in single mode fiber, there is only one path for propagation of the signal or the light which carries the signal. And in multimode, we have many paths. Many means more than one. So because it is traveling in many modes, we need a core whose diameter is very large. So this is the diameter of the core for multimode fiber. Now we'll discuss about the single mode fiber in detail. Single mode cable is a single strand of glass fiber with a diameter of 8.3 to 10 microns. We have already seen in the diagram, the diameter of the core will be very small in single mode cable. So what is the diameter of the core? It is 8.3 to 10 microns. So I can say 8.3 to 10 micron here means micrometer. Micro here represents 10 power minus 6. So 8.3 to 10 into 10 power minus 6 meters. So small the diameter of the core is, so that it will have only one mode of transmission. Now in single mode fiber, it has a relatively narrow diameter through which only one mode will propagate. So what we are seeing, why we are talking about relatively here is, when we compare it with the diameter of the cladding, the diameter of the core is very, very small. We have seen it is of the order of 8.3 to 10 micrometer. So the diameter of the core will be very small, so that only one mode will propagate through it. Then the next thing is, it carries a higher bandwidth than multimode fiber, but requires a light source with a narrow spectral width. The spectral width should be narrow, but the bandwidth is very high. Bandwidth means the range of frequencies through which the signal can pass is very high. So when we compare it with the multimode, the bandwidth for a single mode fiber is very large. This will become one greatest advantage for single mode fiber. Now, single mode fiber has a small diametrical core that allows only one mode of propagation. So we are seeing here, this is the core whose diameter is, it is mentioned 9. We have seen around 8 to 10 micrometer. So this is the diameter of the core. And because of this, what happens? The number of light reflections created as the light passes through the core decreases. So when we are talking about the signal that passes through the core, if you see, if the diameter of the core is very small, I am showing here only the core. This is surrounded by cladding. So this is the core. This is the cladding. And this is the cross-sectional view. So when we are seeing that the signal travels through the core in single mode, there is very little chance for reflections as the light passes. Because of that, what happens? The attenuation is lowered and creating the ability for the signal to travel forward. What happens is, inside the core, when the light travels, more the number of reflections, more the attenuation. Attenuation here talks about the loss of signal or the loss of light. So whenever it is traveling, at each reflection there may be loss of signal. So because it travels in a single mode and the reflections are very less, so the attenuation is less, and because the attenuation is less, the signal can travel farther distances. It can travel larger distances. So this application or this single mode fiber is typically used in long distance transmission and higher bandwidth requirement. So wherever we need higher bandwidth, we use single mode fiber. Wherever it has to be transmitted through long distances, we use single mode fiber. These are the two things we need to remember regarding the single mode optical fiber. So coming to the characteristics, whatever we have discussed, we are going to list them down now. So single mode fiber gives higher transmission rate. So the transmission rate is high. That means it is up to 50 times more than the multimode. When we compare the transmission with multimode, it is 50 times more than multimode. And then single mode fiber has a smaller core than the multimode. This is also one characteristic of single mode fiber. Then the small core and single light wave virtually eliminates any distortion. Distortion means here we talk about the shape of the signal is not changed. So that could result from overlapping of light pulses and providing the least signal attenuation. So there is no loss of signal. There is no change in the shape of the signal. And because of minimum reflections, no, there is less loss also. And so the highest transmission speeds of any optical fiber. So if you see here, what we need to understand is it eliminates distortion, single mode fiber, because it travels along a single path. So it eliminates any distortion because there are very few reflections. So there is no overlapping of the signals or the light pulses. And also the attenuation means the loss of signal is less, and it also has got highest transmission speeds because it is traveling along a straight path. So the transmission speed is also very high. Now coming to the advantages. After the characteristics, whatever characteristics, how we are going to make use of it, how it is going to become an advantage for us. So single mode fiber has a small diametrical core that allows only one mode of light to pass through it at a given time. Then because of this, what happens? The light reflections created as the light passes through it decreases, reducing the attenuation and enabling the light signal to travel farther. So this we have already discussed. So the small diametrical core allows only one mode, and because of a single mode, the reflections are less, and because the reflections are less, it reduces the attenuation, and because it is traveling along a straight path, it can travel farther distances. So this single mode optical fiber is ideal for long distance transmission and also wherever we require more bandwidth, such as telecommunications. So in telecommunications, we require more bandwidth. So all of them, they use these television, cable television providers also use this single mode fiber because it has got a large bandwidth. Now from core to cladding, the diameter ratio is 9 microns to 125. If the diameter of the core is 9 micron, the diameter of the cladding is around 125 micron. This is usually the ratio that we maintain for core cladding diameters. Now coming to the multimode fiber, it has a large diametrical core. So single mode, small diametrical core, multimode, it has a large diametrical core. So that allows multiple modes of light to propagate. If you see in the figure here, this is the diameter, this is the core, and this will become the diameter of the core. So the diameter of the core here is around 50 micrometer. So because of this, what happens? The number of light reflections created as the light passes through the core increases. So what happens? It will be able to create more data to pass through it at a given time. So because the diameter of the core is large, it will allow a number of reflections and also more data can pass through it at a given time. But because of this, what happens? There is high dispersion and attenuation rate. So the quality of the signal is reduced. So with the advantage comes a disadvantage. What is happening here? Because there are multiple reflections, there is dispersion of light and also the attenuation rate, the loss of signal is also high. So because there is loss of signal, the quality of the signal is reduced over long distances. When the signal has to travel a very long distance, and while traveling, if it is undergoing multiple reflections and at each reflection there is a loss of signal or there is attenuation, and because of that, what happens? The quality of the signal is reduced. So this application is typically used for short distances. So like data transfer, audio and video applications in LAN, okay, local area networks, wherever we use it for short distance within a specified area, then we use multimode fiber. It can be typically used for short distances. Now, RF, radio frequency broadband signals, which cable companies commonly use, cannot be transmitted over multimode. We have already seen that in the advantage of single mode fiber. All these cable company operators, where they need large bandwidth, they use single mode fiber. So they cannot use, these cable companies cannot use the multimode fiber. Now multimode cable is made up of glass fiber with a common diameters of 50 to 100 micron range for the light to propagate, and the most common size is 62.5 micrometer, means it is in the range 50 to 100 micron, but the commonly used one is 62.5 micrometer. Then POF, that is power over fiber, is a new plastic based cable which promises the performance similar to a glass cable and for very short runs but at a lower cost. So power over fiber POF cables can be used for carrying a very low power electric signals also. And also when you compare, if you are making a fiber with a glass core covered by the plastic cladding, then the cost may be high. But whenever we are using a plastic based cable, the cost also becomes less. Now we are going to look at the advantages. Multimode fiber gives high bandwidth at high speeds over medium distances. So the distance is a constraint. We are mainly using it for short distances. So for short distances, it can maintain the speed and as well as the bandwidth. Now light waves are dispersed into numerous paths because there are many paths for the light to propagate as they travel through the cable's core. So what is the diameter of the core we have seen? 850 to 1300 nanometer we are writing, or 8.5 to 100 micrometer. Then typical multimode fiber core diameters are 50, 62.5 and 100. So within this range, the most widely used is 62.5, we have already discussed. Now, however, in long cable runs, wherever we have to use long cables, then what happens here is multiple paths of light can cause signal distraction or distortion at the receiving end, resulting in an unclear and incomplete data transmission. So whenever we are using a multimode for long distances, we are using long cables and it is multimode transmission, then the signal gets distorted. So because of this distortion, what happens? The result at the end, the output at the end, whatever we hear or the signal we get is unclear and also it is incomplete. Now, multimode fiber has a relatively large light carrying core. The diameter of the core is large. It is usually used for short distance transmissions with LED based fiber optic equipment. Then single mode fiber has a small light carrying core of 8 to 10 micron. We are doing the comparison between multimode and single mode. So in multimode, what happens? It has large light carrying capacity. Here it is small light carrying capacity because the diameter of the core is small, 8 to 10 micron. Here the diameter of the core is 62.5 micron. And here in multimode, it is used for short distance transmissions, but whereas single mode fiber is used for long distance transmission. Now, if you are doing the comparative study of single mode and multimode fiber, in single mode, there is only one path for propagation. In multimode, there are large number of paths available for light to propagate. And in single mode fiber, the diameter of the core is small, 8 to 9 micrometer. But in multimode, the diameter of the core is 50 to 200 micrometer. And in single mode fibers, there is no dispersion because there is a less chance for reflections through the core. So there is no dispersion. But in multimode, signal distortion and dispersion takes place. Then few more. Signal transmission capacity is less, but single mode fibers are suitable for long distance. The transmission capacity is less, but it is used for long distance communication. Here, because of the large diameter of the core, the signal transmission capacity is more, but it is less suitable for long distance. It is used only for short distance communication. Then launching of light into single mode fiber is difficult because we have already discussed this with the help of acceptance angle. When we are talking about the diameter of the core to be very small, if the light has to enter through the core, so because of small diameter, the launching of the signal into the core becomes very difficult. But in multimode, because the diameter of the core is large, the signal can be launched very easily. Then fabrication cost is very high. Why it is high? Because we need to get very fine diameters of the core, and here the fabrication cost is less. So I hope all the points with regard to the single mode and multimode fibers, and the characteristics as well as the advantages, are done in a comparative study. Now coming to the types of optical fiber based on the variation of refractive index of the core. So the second classification we are doing is based on the refractive index of the core. So based on the refractive index of the core, we are dividing them into two types, the step index and the graded index. First one is step index and the second one is graded index. In all optical fibers, the refractive index of the cladding is uniform. So what we are mainly focusing here is the refractive index of the core. The refractive index of the cladding is uniform. So you might be wondering, when we are talking only about core, what about the cladding? So the cladding refractive index remains uniform throughout the fiber. So what is varying here is only the refractive index of the core. So now we see the step index fiber and this is the graded index fiber, and we are going to discuss about each one of them separately. Based on the mode of propagation of the light rays, the step index fibers are again classified into two types. So what we have seen, the classification here is based on refractive index, we have step index and graded index. Step index and graded index. Now, in step index, based on the mode of propagation, we have single mode and multimode. So we are now going to discuss about step index fiber first, then we will see graded index. Again, in step index fiber, we have single mode step index fiber. This is the single mode under step index. And then we also have the multimode step index fiber. So this is multimode. So in single mode step index fiber, the light rays propagate in a straight line inside the core. So what we have already discussed in single mode, the same thing we are seeing here. So this is a step index fiber. So in step index fiber, we have the core and we have the cladding. These two are the cladding. Core is surrounded by cladding. So this is also cladding. So when the signal passes through the core, what is happening? It travels along a straight line, a single mode. So then we call it as single mode step index fiber. And in multimode step index fiber, the light rays propagate in a zigzag manner inside the core. So if you see, whatever we have seen in multimode, the diameter of the core is very large. You see here, this is the diameter of the core and this is the cladding. So what is happening here is, because of large diameter of the core, the signals, a number of signals, or there are more paths that are available for the signal to transmit. And because of a number of paths, the light travels in a zigzag manner. You can see here, there may be overlap, there may be multiple reflections also. So this is how the light travels in a multimode step index fiber. So if we see the refractive index profile of single mode fiber, so what we need to understand here is, whenever we are talking about step index fiber, what is the refractive index profile of a step index fiber in single mode? The refractive index is uniform throughout the core. So in step index, what we see is the refractive index is uniform throughout the core. Whatever refractive index is there at the center, the same thing will continue till the core cladding interface. So as we go radially in this fiber, the refractive index undergoes a step change at the core cladding interface. So you see here in this diagram, this is the core whose diameter is of the range 8 to 12 micrometer, and this is the diameter of the cladding, 125 micrometer. So you have a core and surrounded by a cladding. Now if you see here, this is the index profile, refractive index profile we are trying to understand. Now whatever the core is, the refractive index of the core is uniform throughout. So this is the core. So we are talking about the refractive index of the core. It is the same throughout, which we call it as N1. N1 is the refractive index of the core. Now from here we have the cladding. So this is the cladding, the refractive index of the cladding. So what we see here is a step change. From here it is varying suddenly. Where is it varying suddenly? Here it is at the core cladding interface. So this is the cladding, this is the cladding, and this is the core. So this is the interface. So at this interface there is a step change in the refractive index. Suppose I am considering a core whose refractive index is 1.5. For example, the refractive index of the core is 1.5. And I've taken the refractive index of the cladding to be 1.46. The refractive index of the core should always be greater than that of the cladding. Now, when I am talking about the core cladding refractive index, so throughout the core, the refractive index is 1.5. But when it comes to this point, the refractive index of the cladding is 1.46. So there is a step change from 1.5 to 1.46. So that is what we are talking about in the refractive index profile. So throughout the core, the refractive index is uniform, and the refractive index of the cladding is also uniform. But when it comes to the interface between the core and the cladding, there is a step change. That is why we call it as step index fiber. So the diameter of the core is about 8 to 10 micrometer, and the diameter of the cladding is 60 to 70 micrometer. And in this fiber, transmission of light is by successive total internal reflections. So what do we understand by total internal reflection? We have discussed it in the principle of optical fiber about total internal reflection. You can refer to the previous videos to understand the principle of propagation in optical fiber. So what we are seeing here is total internal reflection. The light that enters into the core will undergo multiple reflections, and it is getting total internal reflection, so that the loss of signal is not there. And this type of fibers are mainly used in submarine cable systems. So in submarines, they are using mostly this type of fibers. Now, refractive index profile of multimode step index fiber. So in step index, we have two, single mode and multimode. So in single mode, what we have seen, the diameter of the core is small. So the light travels through a single path, and the refractive index, there is a step change in the refractive index. Now here its core and cladding diameters are larger to have. So whenever we talk about multimode, the diameter of the core has to be large so that it will allow many paths for light propagation. The core diameter varies from 50 to 200 micrometer, and the diameter of the cladding varies from 125 to 400 micrometer. And light propagation here is by multiple total internal reflections, because in single mode fiber the reflections are very less. But in multi-mode there are multiple total internal reflections. So we call it as reflective type of fiber, and it is used in data links which have lower bandwidth requirement. So whenever we talk about multi-mode, it has very low bandwidth. So wherever the requirement is of lower bandwidth, we use this. Now we will also discuss about the refractive index profile. So how is the refractive index profile? So since it is also a step index means there is a sudden change in refractive index from core to cladding. So this is the core. The core is surrounded by cladding. Okay, this is the diameter of the core. We are seeing the diameter of the core 50 to 200 micrometer for the core. Surrounded by cladding 125 to 400 micrometer is the cladding. Now here we are going to see the profile, refractive index profile. So for the core, the refractive index is uniform, same throughout. So all this is the core. So what is the refractive index of the core? N1. So whatever the refractive index is here, at this point at the end also, it is the same. So throughout the diameter, it is the same. The refractive index is the same. Now this is the refractive index of the cladding. The refractive index of the cladding is given by N2. Now when you see here, there is a sudden change in refractive index from N1 to N2. That is what we understand in step index fiber. So even in multi-mode, there is a step change in the refractive index between the core and the cladding. Now generally, if you see the transmission of signal in a step index fiber, it is always in a digital form, and it is in the form of ones and zeros. If you are talking about low or no signal, it is 0. High, it is 1. So in multi-mode fiber, the pulse which travels along the path A will reach first at the other end of the fiber. Next, the pulse that travels along the path B reaches the other end. So in multi-mode, what we have seen, that the light travels in a zigzag manner. So we are comparing two signals here. One signal which travels along A, that is along a straight line. And then we are talking about another signal which is traveling in a zigzag manner like this. So this is signal A, which is going along a straight line. And this is signal B, which is going along a zigzag manner. So what happens to the pulse A, which travels along a straight path, will reach first? We all know that the straight line distance is always the shortest distance. So the signal that comes through A will reach the other end. Suppose this is the other end, this is the output. It will reach fast. And later on, this signal B, which is traveling in a zigzag manner, will reach. So what happens then? The pulsed signal received at the other end is broadened. So you have intermodal dispersion. So both the signals are not reaching at the same time. So if you see here, B arrives later than A. So this is what you have for A. So after A reaches, then after a certain time B reaches. So there is broadening of the signal. So because of that, what we have here is intermodal dispersion. So because of that, what happens? There is a limitation on the separation between the pulses, and it also reduces the transmission rate and capacity. The signal also gets distorted. You can see the change in shape of the signal. So because of that, what happens? Due to intermodal dispersion, it reduces the transmission rate as well as the capacity. So to overcome this problem of intermodal dispersion, so whatever problem that is there because of this signals arriving later time, not arriving simultaneously, that can be overcome with the help of graded index fiber. So why the problem is there in step index fiber? Because there is a sudden change in refractive index, and because of that, whatever signals that are traveling, they are arriving at a different time. Because of that, there is intermodal dispersion. So to overcome this problem of intermodal dispersion, we are going for graded index fiber. So what is a graded index fiber? We are going to understand. And again, in graded index fiber, we can have single mode or multi-mode. The same way we had in step index fiber, we had single mode step index fiber and multi-mode step index fiber. In graded index also, we can have single mode graded index fiber and multi-mode graded index fiber. So light rays propagate in the form of skew rays or helical rays. They will never cross the fiber axis. This is the greatest advantage of graded index fiber. So whenever you see the signals here, they are traveling in a smooth helical fashion. They will never cross the axis. So in a helical fashion, they are traveling. So we also call them as skew rays. If you see in this figure clearly, we have the core. This is the core. And this is the cladding. And these are the outer coverings. Okay. This is the light traveling. So in single mode, it may travel along a straight line. But in multi-mode, there may be many modes. And we also take care that the refractive index of the core N1 should be greater than the refractive index of the cladding N2. And here we are seeing a parabolic light path. Without crossing, they are going in a helical fashion. Now, in this fiber, if we try to understand the refractive index profile, how does it differ from step index? The refractive index decreases continuously from the center radially to the surface of the core. So, here we have seen this is the core. This is the diameter of the core, 50 to 100 micrometer. And surrounding the core, we have the cladding. The diameter of the cladding is 125 to 140. So when I talk about the diameter of the core, and you see the refractive index of the core. So at the center, the refractive index, say R is equal to 0. And as you go from the center towards the edge of the core, the refractive index becomes A. So there is a gradual change in refractive index because at the center, if you are considering 0 and gradually increasing to A. So the diameter of the core varies from 50 to 200 micrometer and the diameter of the cladding varies from 125 to 140 micrometer. But what happens? The refractive index is maximum at the center and minimum at the surface of the core. So here we are talking about the core. The refractive index is not uniform throughout. So if we take at the center, it is maximum. And as you go away from the center diametrically, means in this fashion. So the diameter, as the diameter varies, the refractive index also varies. So at the center, it is maximum. Say we have taken 1.5. So gradually it will decrease from 1.5 to 1.49, 1.48, 47, so on. By the time it comes here, it may come to 1.45. So gradually the refractive index decreases. So it is maximum at the center and minimum at the surface of the core. And the refractive index profile is circularly symmetric. Circularly symmetric in the sense, whatever the refractive index we have here is the same at the diametrically opposite end. So circularly symmetric. So on this circle inside the refractive index is the same. And the next one, it reduces slightly but diametrically symmetric. Now what we see here is the refractive index changes continuously radially in the core. So light rays suffer continuous refraction. So what we are seeing here is refraction. The propagation of light is not due to total internal reflection, but refraction. We know what happens in refraction. Whenever there is a change in medium or there is a change in refractive index, there is a bending of the light ray. And this phenomenon we call it as refraction. So here, because we are seeing that the refractive index of the core varies gradually, changes, because of that there is continuous refraction. So in graded index fiber, the light rays travel at different speeds in different parts of the fiber. We know when a light ray travels from one medium to the other medium or from one refractive index to the other refractive index, the speed of light varies. So here also, because the refractive index varies, the speed of light or the speed of the signal also varies. So near the surface of the core, the refractive index is lower. So at the center, the refractive index is maximum, and towards the surface, it is going on decreasing. So at the surface of the core, the refractive index is low, and near the outer surface, the rays will travel faster. Because the refractive index is less, they will travel faster. Now, because of this, all the rays arrive approximately at the same time. What we understand here is, at the center where the refractive index is high, more, the light rays will travel slowly. But when you come to the surface of the core, because the refractive index is less, they will travel faster. So those rays which are traveling a larger path are traveling fast, thereby arriving at the same time. So if you see here in this diagram, this is the point where the refractive index is maximum, the light rays traveling. Here, because the refractive index is maximum, this ray will travel slowly. And as you go away, that is towards the surface, the refractive index is very slow here, less here. So this signal will travel fast. So the one which is traveling straight is going slow, but the one which is traveling a larger path is traveling faster. So they both arrive at the same time. So consider a ray denoted by path 1 along the axis of the fiber and two more rays along path 2 and 3. So along the axis of the fiber, the refractive index of the core is maximum. This we have seen. So what happens to the speed of the ray? It is less. Because the refractive index of the core is maximum, the speed of the ray is less. But when we talk about paths 2 and 3, they are traveling in a sinusoidal fashion. They will travel a longer path. They have a longer path. So these rays travel in low refractive region because at the surface the refractive index is less when compared to the center, which is maximum. So they move slightly faster. So the pulses of signals that travel along path 1, 2 and 3 reach the other end simultaneously. The one which is traveling along the higher refractive index at the center is traveling slowly. The one which is coming from the surface, which is having a less refractive index, is traveling faster. So what happens? They reach simultaneously. So the problem of intermodal dispersion. What is intermodal dispersion? Here the signals, when they arrive at the output at different times, there may be the spreading of the signal, which creates lot of distortion, which we are calling here it as intermodal dispersion. So that problem can be reduced to a large extent using graded index fiber. So that is the main difference between step index and graded index. In step index, there is a step change. Means when it comes from the core to the cladding, there is a sudden change in refractive index. Because of that, there is intermodal dispersion because the light rays are arriving at different times. But in graded index, we are arranging the refractive index in such a way that all the signals will arrive at the output at the same time, so that this problem of intermodal dispersion can be eliminated. So we also have the comparative study between the step index graded fiber, step index fiber and the graded index fiber. The refractive index of the core is uniform in step index fiber. And there is an abrupt change in refractive index at the core cladding interface. So from the core to the cladding, there is a change in refractive index. But here, the refractive index of the core is non-uniform. How it is non-uniform? At the center, it is maximum, and as you go away from the center, it goes on decreasing. So what happens? It decreases parabolically from the axis to the surface. So the light rays propagate in a zigzag manner inside the core, and the rays cross the fiber axis for every reflection. So they may cross each other and travel in zigzag fashion. But here in graded index, they propagate in a smooth fashion, sinusoidal fashion in the form of helical rays, and they will never cross the fiber axis. And in step index fiber, the signal distortion is more in multimode. In step index also, if you see the multimode step index fiber, the signal distortion is more and there is no distortion in single mode. But in graded index fiber, signal distortion is very low, even though the rays travel at different speeds inside the fiber. So we have seen, depending upon the refractive index, the speed of the signal also varies. But even then, the signal distortion is very less. Now, the bandwidth of the step index fiber is about 50 megahertz for multimode fiber, and it is more than 1000 megahertz in case of single mode fiber. When it comes to graded index fiber, it is 200 megahertz to 600 megahertz. Okay, and the attenuation of light rays is more in multimode fiber. Attenuation here is the loss of the signal, and attenuation of the light rays is less in graded index fiber. Then the numerical aperture of a multimode fiber is more, but in single mode fiber it is less. Numerical aperture here always represents the angle or the mode of propagation for the signal to travel through the optical fiber. More the numerical aperture, more easily it can travel. The numerical aperture of a graded index fiber is less. So, if you want to have more reference for the differences between step index and graded index fiber, or the multimode and single mode fibers, you can refer to books by P.K. Palaniswamy, Engineering Physics, and Engineering Physics by Gaur and Gupta. Thank you, and see you in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.